Welcome to your Biostatistics course. Today, we are diving into one of the most powerful tools in a scientist's toolkit, linear regression analysis. Imagine you are a doctor, noticing that as patients age, their blood pressure rises. What if you could predict a patient's exact blood pressure just by knowing their age? That is exactly what linear regression allows us to do. It takes our scattered real-world observations and turns them into a precise mathematical rule, allowing us to forecast the future. Let us get started. Now that we know our goal is to make predictions, let us understand what linear regression actually is. In biostatistics, it is a method used to model the relationship between two different things. The word linear is key here because we are assuming that the relationship between these variables can be represented by a perfectly straight line. Think of it like drawing a straight line through a scattered flock of birds to guess where the next bird will appear. Our main objective is to find the specific straight line that best fits our scattered data points. We do this by minimizing the distance between the actual data we have collected and the line we are predicting. Before we draw our line, we need to define the two types of information we are working with. Every linear regression has a dependent variable and an independent variable. The dependent variable, often called the outcome or response, is the exact thing we are trying to predict. The independent variable, or the predictor, is the information we already have in our hands. Why does this matter? Because without defining these, we cannot make actionable predictions. For instance, a pharmacologist uses the known drug dosage, the independent variable, to predict the unknown tumor shrinkage, the dependent variable. An ecologist might use average summer temperature to predict an endangered species population. We are using what we know to reveal what we do not know. Now that we understand our variables, let us look at the mathematical equation that describes our straight line. You might remember from basic algebra that any straight line on a graph can be described by a simple equation. In biostatistics, we use the formula y equals a plus b times x. Let us break down every piece. Y is our dependent variable, the outcome we are trying to predict. X is our independent variable, the data we already know. The letter A represents the y-intercept, which tells us the predicted value of y when x is exactly 0. Finally, the letter B is the slope of the line. The slope tells us exactly how much y is expected to change for every single unit increase in x. If b is positive, y goes up as x goes up. If b is negative, y goes down. To truly grasp this equation, let us visualize what it looks like on a graph. Here, you are seeing a scatter plot of data points, representing our real-world observations. The horizontal axis represents our independent variable, x, and the vertical axis represents our dependent variable, y. Notice the solid red line cutting right through the middle of the scattered blue dots. That is our line of best fit. Look at where the red line crosses the vertical axis on the left. That specific point is our intercept, A. Now look at the small triangle drawn on the line, labeled rise and run. This represents our slope, B. It visually shows how much the line rises for every step it moves to the right. This single line minimizes the total distance from all the scattered dots, giving us the most accurate prediction possible. With our visual intuition built, we must now ask, how do we actually calculate that perfect slope from raw data? We use a method called least squares, and it gives us this specific formula for the slope, b. While it looks complex, it simply compares how X and Y change together versus how X changes on its own. Let us define the symbols. The letter N represents the total number of data points in our sample. The sum of xy means we multiply each x value by its corresponding y value and then add all those products together. The sum of x and the sum of y are just the totals of our individual variables. The denominator measures the spread of the x values. When the top part of this fraction increases, meaning the variables move together strongly, our slope becomes steeper. Once we have calculated the slope, finding the starting point of our line is much easier. Because the line of best fit must always pass through the exact center of our data, we use the averages of our variables to find the y-intercept, A. In this formula, y bar represents the mean, or average, of all our dependent variable values. X bar represents the mean of all our independent variable values. The letter B is the slope we just calculated. This formula is essentially saying that to find our starting point, we take the average y value and subtract the effect of the slope multiplied by the average x value. If the average y increases, the intercept shifts upward, moving the entire line higher on the graph. Before we move on to abstract concepts, let us see this with a concrete medical example. Suppose we want to predict a patient's blood pressure based on their age. We have data from 3 patients. Patient 1 is 40 years old with a pressure of 120. Patient 2 is 50 with a pressure of 130. Patient 3 is 60 with a pressure of 140. We want to predict the pressure for a new 70-year-old patient. First, we identify our variables. Age is X, blood pressure is Y, and N equals 3. We start by calculating our foundational building blocks. We add up all the ages to get a sum of 150. We add the blood pressures to get 390. We multiply each age by its pressure and sum them to get 19,700. Finally, we square each age and sum them to get 7,700. These sums are the engine of our calculation. Now that we have our sums, we can plug them into our slope formula to see how age and blood pressure move together. We substitute N equals 3, our sum of xy, our sum of x, and our sum of y into the numerator. In the denominator, we plug in our sum of x squared and the square of our sum of x. When we multiply these out, the numerator becomes 59,100 minus 58,500, which simplifies to 600. The denominator becomes 23,100 minus 22,500, which also simplifies to 600. Dividing these gives us a slope of exactly 1. Physically, this means that for every 1-year increase in a patient's age, their systolic blood pressure increases by exactly 1 unit. With our slope calculated, we are ready to find the intercept and make our final prediction. First, we find the average age by dividing 150 by 3, giving us 50. We find the average blood pressure by dividing 390 by 3, giving us 130. To find the intercept, A, we take the average blood pressure of 130 and subtract our slope of 1 multiplied by the average age of 50. This gives us a y-intercept of 80. Our final predictive equation is y equals 80 plus 1 times x. Now we can answer our original question. What is the blood pressure of a 70-year-old patient? We simply plug 70 in for x. 80 plus 70 gives us 150. We have successfully used linear regression to forecast a biological outcome. To solidify your understanding, let us look at an agricultural biology example. A botanist applies different amounts of nitrogen fertilizer to 4 identical plants to see how it affects their height. Our independent variable, x, is the fertilizer in grams, 1, 2, 3, and 4. Our dependent variable, y, is the plant height in centimeters, 4, 5, 7, and 8. We want to predict the height of a plant receiving 5 grams of fertilizer. Just like before, we quickly calculate our sums. The sum of the fertilizer amounts is 10. The sum of the heights is 24. Multiplying each pair and adding them gives a sum of products equal to 67. Finally, squaring the fertilizer amounts and adding them gives 30. These 4 numbers are all we need to build our model. Using the sums we just found, we can determine how fertilizer impacts plant growth by calculating the slope. We plug our values into the formula with n equal to 4. The numerator becomes 4 times 67 minus 10 times 24. This simplifies to 268 minus 240, leaving us with 28. The denominator becomes 4 times 30 minus 10 squared. This simplifies to 120 minus 100, leaving us with 20. Dividing 28 by 20 gives us a slope of 1.4. This is a very useful biological insight on its own. It tells the botanist that for every single additional gram of fertilizer applied, the plant grows an extra 1.4 centimeters. Now that we have our slope, let us finish our equation and make our prediction. We find the intercept by taking the average plant height, which is 6, and subtracting the slope of 1.4 multiplied by the average fertilizer amount, which is 2.5. This gives us an intercept of 2.5. Our final predictive equation is y equals 2.5 plus 1.4 times x. To predict the height of a plant receiving 5 grams of fertilizer, we substitute 5 for x in our equation. 1.4 times 5 is 7, plus 2.5 gives us a predicted height of 9.5 centimeters. This perfectly demonstrates how regression allows biologists to estimate outcomes for conditions they have not even tested yet. We have covered a lot of ground today, so let us summarize the key takeaways. First, linear regression is a powerful statistical tool that draws a mathematical line of best fit through scattered data points. Second, by calculating the slope and the y-intercept, we create an equation that models the exact relationship between an independent predictor and a dependent outcome. Finally, this simple equation, y equals a plus b times x, allows scientists and doctors to move beyond simple observation and make highly accurate, data-driven predictions about the real world. Mastering this concept is a massive step forward in your journey to understanding biostatistics. Keep practicing these calculations, and you will see these patterns everywhere in biology.